Good afternoon. Thank you for being here. Day 4 in the afternoon, after lunch, during exhibit hall teardown. So I really appreciate you being here, and I want to recognize your tenacity on this topic. As Dimitri mentioned, my name is Kevin Moran. I'm with Abaco Systems, and today I'm going to be talking about the opportunities and challenges with vision systems in defense applications, particularly under very difficult, diminished environmental type situations. The topics I'll cover, I'll give a little bit of an overview of Abaco. We're kind of new in terms of this particular brand, but we're out of GE Intelligent Platforms. I'll highlight a couple of relevant products that include NVIDIA GPUs. And then I want to do a little bit of an overview on what's going on in defense with R&D as it relates to autonomous vision systems, because AI will literally change the face of defense over time. And this is not the kind of event where defense is featured super prominently. I mean, it is here, but there may be people who are involved in defense, people who aren't involved in defense but curious. And so I just want to provide a little bit of overview because there's exciting things going on. And then I'm going to talk about our ImageFlex toolkit, which is a unique and very innovative image processing, image visualization toolkit with APIs that greatly reduce the coding effort to create these different high-performing real-time vision applications and also visualization, which is available in our products. It's baked right into the product. So with that, I'll go ahead. So Abaco Systems, our bread and butter is high-performance embedded computers for military aerospace applications. These are highly ruggedized, size, weight, and power optimized. We have a global footprint, over 800 employees worldwide. By the way, you take all the pictures you want, but these will be posted, as well. So, but feel free. Our main engineering centers are in Huntsville, Alabama, near the Redstone Armory, Redstone Rocket Program, Apollo, etc., and Toaster, UK. If you look at the breadth of products we have everything ranging from single board computers, sensor image processing, mission-ready systems, highly ruggedized, high-speed 10 gig managed Ethernet network communications, high-performance embedded computing, etc. And today we're going to really focus on graphics and video products. I mentioned a couple of relevant products. What we're showcasing here actually in our booth are the GVC1000, which includes Tegra TX2, and then Lightning GVC2000, which is a GM107 GPU plus Xeon D CPU. So it's a two-board solution that's about this big. Again, this is very rugged equipment. Operating from -40 to +71 C. So this is not consumer grade, more industrial grade, approaching automotive grade, etc. Highly reliable. Oh, it's kind of oh, well, there's a little bit of wrap there. But anyway, the vision applications supported by the GVC1000 and 2000 range from image recognition, segmentation, object localization, image fusion from multi-sensors, image stabilization, target tracking, image correction, distortion correction, and morphing, and situational awareness, 360-degree type spherical situational awareness that we can create. So when we talk about autonomous, that means many things to many people, I find. And there's a lot of things that are used in the military where they say unmanned or guided or so forth. So I thought we'd take a step back and talk about what autonomous really means in terms of military and what they're trying to accomplish over time in terms of enhancing the workforce effectiveness or the fighting force effectiveness, as well as improving their capabilities in intelligence, surveillance, and reconnaissance. So the Oxford Dictionary has definitions for autonomous, and that's freedom to govern itself, control its own affairs, freedom to act independently, or in terms of machines, devices capable of operating without direct human control. But it is not just automated, where something is pre-programmed to do something over and over again. It's not remotely operated, using a joystick, etc., from remote, or guided. So I think for our purposes in the military, what they're trying to accomplish through autonomous is the ability to conduct complex, cooperative, extended missions within very broad objectives, principles, and guidelines. Go out there and solve a problem. Okay, a very diverse set of machines, maybe in cooperation with human beings, but they have a mission to do with very little or no human intervention. Now, probably people know this, or they don't remember it, or this happened before you were born in some cases. But Carnegie Mellon built an Army vehicle, a road-based Army vehicle that had autonomous capabilities for road following called ALVIN. Autonomous land vehicle in a neural network, 3-layer backpropagation network, etc. This work was done in 1985 to 1988. It resulted in a report that was issued through DARPA, the Defense Advanced Research Project Agency. On 90, you can download it. It's a pretty good read. But that really was the origin of a lot of things we're seeing in terms of autonomous vehicles. Because here's an actual Super 8 movie of it. And by the way, it goes around and around and around, and it never veers. It might be because actually this video is looped. But 1988, so 30 years ago. So what happened is that DARPA created these challenges, Grand Challenge, Urban Challenge, et cetera, and it led to commercialization or commercial applications in the private sector of these capabilities. It's something they wanted to encourage. They put up these competitions. They had very nice prizes. And the third challenge, the Urban Challenge, which was a vehicle that, the first vehicle to actually complete a pretty complex course in an urban setting that was actually private and off-road, was a Chevy Tahoe. And in partnership with Caterpillar, Continental, Velodyne LiDAR, 64 beam you see up there, and again, Carnegie Mellon. Fast forward, in 2014, we have a Tesla autopilot. Some people could argue that's level 2 or level 3 automation. And then today you have this wealth of use cases going on, okay, ranging from robotaxis, which are really point-to-point ad hoc, robotrams, which are fixed routes. That vehicle is in autonomy in Singapore. This is a Navia tram built in France. Robo Pizza, this is really delivery. We're looking at delivery, and so is Amazon. This is a collaboration between Ford Motor Company, Argo AI, and Domino's Pizza. And then Robo Beer. This is really freight logistics long haul. And this is a picture of an Otto truck. It's a Volvo truck equipped by Otto, which got acquired by Uber. And they hauled a trailer full of Budweiser beer across Colorado, actually at night. And what's not to like about pizza and beer? Oh, why is this not advancing? There we go. But, you know, unbeknownst to many, or kind of unseen by many, the same thing has been going on in defense and military. So we start with the same ALVIN in '88. In that same DARPA Urban Challenge in 2007, Oshkosh entered a truck called the Terramax. Fast forward to 2014, this really occurred later, or earlier, but you know, here's a view of the kind of the head-up display, virtual reality, augmented reality display in an F-35, Lockheed Martin, circa 2014. I just picked that because it's the same year as the Tesla. But then look at the applications that are going on in terms of autonomous now. You have this autonomous platform. By the way, am I in your way? Okay. You have this autonomous platform in the Army, and that you can put any kind of vehicle on top of this, whether it's hauling something or it's got weaponry, et cetera. Autonomous underwater vehicle, this is a sub-hunter. This Boeing QF-16, this is a recommissioned F-16 that flies autonomously, and right now it's used for target practice. And then robot pack mules. They can handle like 300 or 400 pounds and traverse terrain that a wheeled vehicle couldn't. So the point is, you can think about all the different business cases that are going on in terms of commercial vehicles. And those are business cases really intended to reduce labor costs as much as there are safety benefits that could accrue. But if you look at what's going on in land, sea, and air, the environments are different, the missions are different, and the environments they're operating in are very, very different. Think of underwater, 40,000 feet, all kinds of hostile terrain, et cetera. So I mentioned earlier that AI will transform the face of defense, and here's some of the areas, just a few of the areas they're really looking at that you should consider diving into or looking into. But logistics, hauling material to the front lines with driverless vehicles, or truck platooning, augmented reality displays, wearables, intelligence, surveillance, and reconnaissance type drones. And then in terms of actual warfare, electronic warfare, these are RF signals that are used to spoof or jam the enemy. And right now, if a plane receives a new signal it hasn't seen before, sometimes the mission is aborted, and those signals have to be analyzed over a long period of time in supercomputers. And the goal is, can we deal with these new signals on the fly and create a countermeasure on the fly and keep the mission going? Collaborative missions, this is human beings interacting or collaborating with machines that can go out in front of a mission or a campaign and do the early exploration, look for improvised explosive devices, you name it, before the humans come in. Guided missiles, of course. And then in terms of the kind of the back office work, wargaming and planning, right? This is very strategic. And then cybersecurity, resiliency, big data, cloud computing. So these are just some of the areas that the defense is spending on right now. In fact, there's a DoD Unmanned Systems roadmap that was published in 2014. Again, I recommend people download this. But it kind of highlights the activities that are going on in the different fields, whether it's air, ground, maritime, and how much is being spent in terms of research for unmanned systems. And down here in the lower right, $24 billion over 5 years allocated for unmanned systems through 2018. That's only going to grow going forward. And in terms of the intent and the points, the things they want to accomplish, here's some points that you can extract out of the text in the roadmap. But their definition of an autonomous system is self-directed to reach a human-directed goal. Machine learning autonomous systems can develop modified strategies. So they're not just programmed. In unforeseen situations, the autonomous system finds the optimal solution. Smart teams of unmanned systems operating autonomously conduct operations in contested environments. And this last point is very key. Industry and academic partnerships will be critical. They're really reaching out to the development community. They're collaborating with automotive, et cetera. They want to find the best practices and kind of move down the learning curve as quickly as possible. So they're not trying to be very insular about the research they're doing. They're being very open. So some examples in the different environments, land, sea, and air. A lot of research is going on, land through the U.S. Army, TARDEC and CERDEC. They have cooperative task trucks, robotic sentries. I showed you the legged squad support earlier. Office of Naval Research in the middle, swarm patrol boats that protect harbors. Sea Hunter, this is a surface submarine hunter, and then underwater unmanned vehicle. In air, the Air Force Research Laboratory. I showed the Boeing autonomous F-16 earlier. And then through a research project with the Air Force Research Laboratory, Sikorsky has automated a helicopter called Sarah and a Cessna 208 plane called DARPA Alias. And these two can fly around in tandem in a kind of a choreographed way without any human intervention whatsoever. And I want to focus a little bit on swarms because there's technology that's crossing all these modes from land, sea, and air. So the Air Force, there's looking to implement predator swarms that can kind of react on the fly. Army robotic sentries, these can protect a base. They can be almost like junkyard dogs that would be vigilantly waiting, and if something moves that shouldn't be moving, they can go and investigate. Based on learning over time, they can know what kind of patterns exist in terms of human movement, or what trucks come in at what time, and if something's different, they can react to it. Navy swarm patrol boats, these can protect the harbor, or they can literally go along with a warship, and if the enemy approaches, these swarm boats can actually peel off on their own, surround the enemy, neutralize the enemy, and if they need to, go from a defensive to an offensive posture, if you know what that means. So these swarms, they're given a very broad cooperative mission. They're not programmed or automated. The control's decentralized. They learn continuously over time. They extend the communications beyond the line of sight, and they're patrolling 24/7. Somebody can set these things up in a harbor, and maybe it takes a week or a month, and then they just leave it, and nobody has to intervene for a year. They do what they do. There's a couple of neat YouTube videos. I'm not going to go into them. I don't want to try any internet connectivity here, but Swarm and MDARS, modular defense vehicles, is the Army. But there's plenty of videos online that you can look at. The Swarm patrol boats in particular is fascinating to watch. Whether we're talking autonomous vehicles or we're talking augmented reality, it comes back to vision and perception. That's where it begins, and then you get to decision making and execution. So a vehicle is reliant on multi-sensor array, radar, LiDAR, camera, ultrasonic. But with augmented reality displays, you have to add registration and stabilization. In a car that has an inertial measurement unit and GPS, things can be referenced against GPS, the geolocation. Not so with augmented reality displays. They have to self-register without GPS. And then just to compare the two environments between the road-based world that we hear so much about and what is going on in terms of military, if you're talking about self-driving vehicles, you're pretty much talking about a flat Earth, right, with 2D localization primarily. You don't have actively hostile threats, typically, unless there's road rage. Stable terrain, you're operating on stable terrain unless there's an earthquake. And it's kind of blue skies application, right? Blue skies are good for these kinds of vehicles. But skies are not always blue, okay? And today, the remedy for this situation in terms of a self-driving car is stay home. That's the remedy today. You can't stay home, in war. You have to go to war. You're going to be in contested environments. It's a 3D world, contested space, threats from all directions, explosions, altered terrain, degraded visual environments, smoke, fire, sand from Black Hawk helicopters, et cetera. Very, very tough to operate in this environment, and obviously very mission critical. So that brings me to AXIS. So AXIS is a unique tool suite created by Abaco Systems, and it includes everything from, high performance libraries, performance communications libraries, performance analysis, how to take your topography or your architecture and get the biggest bang for the buck in terms of performance, data flow, and application GUI. And today I'm really going to focus on ImageFlex. See how I'm doing on time here. Oh, I'm pretty good. So I mentioned earlier, ImageFlex, it's an image processing and visualization toolkit. It has APIs designed to greatly reduce the coding workload to create high-performing applications for image processing, image visualization applications, and the different things that you have to do, whether it's in a vehicle or whether it's goggles and wearables and so forth. Part of the key is to offer interoperability between CUDA, OpenGL, OpenCL. So a lot of the code that people would have to write to do those transforms or get things to interoperate between CUDA and OpenGL are already in ImageFlex. And ImageFlex is baked into our GPS products. It comes with it. So where would ImageFlex be relevant? Electro-optical and infrared video processing and helmet-mounted displays. I'll show a video of that. Degraded visual environments, multi-sensor fusion, 360 spherical situational awareness, and autonomous systems and computer visions, including AI and deep learning. So here's some general vision solutions that I'm going to highlight. Actually, this is all of them. Neural network classification, target classification, object detection, CUDA interoperability, adaptive image fusion, GPS stabilization, image morphing, situational awareness. So I want to highlight each of these individually, tell you a little bit about what's behind the application, and then show you a video of it in action. So neural network classification. This really demonstrates the integration of an AI classifier into an ImageFlex application. It uses pre-trained cafe-based GoogleNet neural network, but then it's converted to an optimized inference engine via an ImageFlex conversion utility. and in turn uses NVIDIA's TensorRT. We also have an annotator tool that's part of it that makes annotation of each image more streamlined, more efficient. And I'm going to show you like a 20-second video now, and I want to prepare you for what you're going to see and what I want you to look at. You'll see the video, but down at the bottom there will be 3 fields. And the field on the left will have algorithm information. It'll have the lines of code that were used for that application. You'll have frames per second, et cetera, or the kind of the bit map of the image. In the middle, you'll see the CPU cores, and on the right-hand side, you'll see the GPU processing. And the point with this is that we want to have the GPU doing the heavy lifting, and we want to kind of minimize the workload on the CPU cores. And that's what CPUs are built to do, and that's what we want to optimize. And again, with this ImageFlex toolkit, you can revise your algorithms and look at the performance and look at CPU versus GPU loading until you get to a point of optimization. It worked. So 525 lines of code for object classification. You see on the top the identification, 80% warplane, military plane. When it flips, it'll pick up the wing. And then when the plane's gone, it becomes a sandbar. And again, you have these utilities where you can analyze the performance and the allocation of processing power between CPU cores and the GPU. Sure. So once we've classified objects, we want to detect them, right? And again, we have an API for that. This next video will demonstrate the integration of our AI object detection into the ImageFlex application. It's using NVIDIA's DetectNet object detection neural network. And as per the simple classifier, this is converted into an optimized inference engine via ImageFlex conversion utility that uses TensorRT. And ImageFlex is also what's being used to draw the bounding boxes around the vehicle and set the confidence level or the probability level. So in this next video, any vehicle that's 60% probably a car will have a bounding box put around it. And again, notice the GPU usage versus the CPU core loading. You'll see a couple of cars come in from the left, and you'll see how quickly they get picked up and identified as cars. So that's a very oblique view. Should I run that again, or move on? Okay. CUDA interoperability. Again, ImageFlex is using a simple API to facilitate ImageFlex interoperability. This particular example is CUDA to OpenGL. And you'll see down here, these are some of the interop applications or features, functions that are created in terms of buffering, texturing, registration, et cetera, between CUDA and OpenGL. And the video is going to show edge detection. This is a real camera image. This is edge detection processed through ImageFlex. And this is really what you need. Edge detection is where identifying an object and then dealing with that object really begins at edge detection. We can also take these same images and put them onto spheres and do all kinds of other morphing and manipulation of the vision system as well between CUDA and ImageFlex. Adaptive image fusion. This is something that I really like to watch maybe over and over again. But this is taking diverse sensors. In this case, it's a camera or electro-optical and then infrared heat sensors. And if you think about what can go on in battle or even like a wildfire, smoke can completely obscure your vision. but infrared can pick up differences. Even within a cloud, you can detect human beings and other kinds of objects. So we have two types of fusion modes available: alpha blend, which is simple weighted combination of two input images, and then adaptive fusion, designed to maintain high resolution detail of both images. It provides a per pixel frequency cut and other fusion weightings, enables tailoring to best meet the fusion demands of the application and the sensor attributes. And this is using OpenGL shader language, GLSL, GPU agnostic, and again, minimal CPU overhead. When I play the video, train your eye for a bit on the camera image and the IR image at the top, and you'll see people moving around through the smoke. You'll see projectiles that you can't see at all with the camera, but in the fused image, it becomes very apparent, very clear. So you'll see people start to come out of the building and some projectiles. Oh, there's a projectile. You can't see anything in the smoke at all. But if you're wearing goggles, you get the composite view. And again, has to be perfectly registered, very low latency. It'd be impossible to deal with it with the naked eye. Lines of code, 150. Okay, we've done some comparisons between ImageFlex, OpenGL, and CUDA. If this were CUDA or OpenGL, it would be on the order of 1,200 lines of code. So part of this is to simplify the task, reduce the cost, and increase your time to market. Or actually, reduce your time to market. Augmented reality displays, here's another 3 or so kind of vignettes. GPU stabilization uses a CUDA-optimized algorithm to stabilize video, correcting for shake in horizontal and vertical planes and rotational zooms. Based on the Lucas-Kinnaid method, I really can't go into it, but here's the kind of the flow diagram for the algorithm. This is a bicyclist, and the image on the right is the stabilized one. And so you see the frame moving around, but the features of interest are stabilized in terms of reduction in movement and bouncing, vibration, etc. So again, whether you're wearing a helmet or whether you're a vehicle that's trying to navigate this terrain, becomes highly relevant. Distortion correction, image morphing. This has to do with head-up displays, augmented reality displays, could be goggles where the image has to fit the shape of the goggles without causing distortion, etc. So this is a simple barrel pincushion distortion correction, or complex adaptive correction via morphing per a grid. A more complex grid can morph into arbitrary shape to compensate for eyepieces or complex optics. And then each subrectangle in the grid can morph in 3 different ways to suit the requirements, from project to triangle linear to quad linear. Again, note the minimal usage of the CPU cores. Lines of code 200 through the ImageFlex API. And then situational awareness. ImageFlex provides the API to create and draw cube maps. And this gives us the capability to generate a full or partial skybox from the live camera array. Facilitates real-time 360-degree or fully spherical situation awareness applications via camera stitching. And the configuration utility enables setup of stitch skybox panoramic from camera array and capture configuration parameters for the skybox application. In the video, you'll see 3 different kind of views that I'll describe. Created. So the top is equirectangular map, the left horizon view, and then bird's eye view. If you're not in the air, but you can see things from the air, based on the field of view created by your sensors, whether it's cameras, LiDAR, radar, etc., and how that's fused. Again, 315 lines of code. So just to wrap up, my message is that defense is vital to security. You know, we can make long-term investments in technology because the people who invest in that technology will get the benefit of it over time because we have a stable society. And our countries are stable when they have security and they have defense. And GPU-enabled deep learning graphics and vision systems are critical in military. It will transform the defense, and the opportunities for developments are incredible and incredibly important. And that's it. Thank you.